For example 3, we're asked to write a function that models the given data. So this function, just taking a look at this, the x's are going up by 2's over and over and over. Let's take a look at the y values. So our y values are changed in our y values, looking at our first differences, going from 110 to 141, that's plus 31. From 141 to 176, that's plus 35. 176 to 215, that's plus 39. From 215 to 258 is plus 43. From 258 to 305, that's plus 47. And from 305 to 356, that's plus 51. So those aren't constant, not linear. Let's try again. Going from 31 to 35, that's plus 4. 35 to 39, that's also plus 4. 39 to 43, you're noticing a pattern. It's a bunch of plus 4s. 43 to 47, plus 4. 47 to 51, plus 4. So therefore, it is quadratic. Now, in order to come up with a function for it, we're going to use a graphing calculator. Now, for simplicity's sake, I'm just going to use Desmos. It's a little easier for me to show on my computer. So, on Desmos, I have it set up, and I'll share this link with you as well. I have it set up where I can just type the information here, type in the x values into here, the y values into here, and it automatically comes up with an equation for us. So like you'll even see it shows what it would look like as a cubic, a quartic, and a exponential. It also shows that the cubic is also an r squared of 1, which is really good. Look at that a value. That's negative 5.199 times 10 to the negative 17. That's stupid small. That's 0.000000519. Also, it's negative. But anyways, the quadratic is perfect. It's spot on. Let's write that down. So our equation for that ends up being, sorry, waiting for error survey to pick back up. There we go. So the equation for it is y equals 0.5x squared plus 2.5x plus 8. Again, you can use your graphing calculator, plug that into stat, then do the quadratic regression. Now the last thing we're going to take a look at is related to that, but sometimes it's not as easy to figure out like, oh, it's clearly quadratic, so therefore you should quadratic model. So when data are not ordered or evenly spaced, you may have to try several models to determine the best approximates for that data. Graphing calculators often indicate the value of the coefficient of determination, indicated by r squared, or capital R squared. The closer it is to 1, or technically negative 1, the better. So here's a set of data. We're asked to write a function that models this given data with the populations of some town. I'm going to go on a limb and say it's probably not just 400, maybe it's 400,000, but for what we're dealing with here, this is going to be good enough. So in 1990, the population was 400. In 1993, it was 490. 1997, 642, etc., etc., etc. Folks, one suggestion, especially when dealing with years 1990, 1993, those all work out, but it'll end up making our equation a little nastier. So I'm going to say, let's make 1990, let's make that year 0, which would make 1993 year 3. 1997 would be year 7. 2000 would be 10 years later. 2002 would be 12 years later. 2005 would be 15. And 2006 would be 16 years later. So using this information, I again went to Desmos and typed in that information. Now this one, you'd have to type it into your graphing calculator using stat, check out the various regressions, linear, quadratic, cubic, and also quartic and exponential. Sorry, I forgot which one I was saying. But on Desmos, I have it set up. Here's the one I'm looking at. I already typed that information in using the years from 0 to 16 for 1990 to 2006. I typed in the populations, and now let's take a look at our r squared values. So for quadratic here, I'm going to zoom in a little bit here. For quadratic, that's pretty good. That's an r squared of 0.9998. Not bad. The cubic, it's 1. Now, one challenging thing is it's probably not perfectly 1, and that's not bad. For quartic, it says it's 1. It's probably not perfectly 1, but it's got a really annoying a value, so a really small leading coefficient. For what I would probably use in this one, I would probably use exponential, especially considering populations are often exponential. So this I would use as our exponential, 399.905. And then I would use maybe the first 2 decimal places here. So I would do 399.91 as my A value, 1.07 as my B value. Let's jump back into that and jot that down. So, sorry, waiting for error server to pick back up. I would say population as a function of time is about 399.91 times 1.07 to the t power. In other words, they're gaining about 7% of their population every year.